and these are the universities in quantum amplitude amplification and quantum algorithms. For the quantum circuits and digital logic, quantum logic, we can see here Egypt, Algeria, Tunisia. So we have a big network working in these topics with good output. So we need to collaborate to make this much better. These are the universities in quantum logic. In terms of quantum cryptography, we have Egypt, Morocco, and I'm glad that actually I can see Egypt here in the first place, not in all topics. I will show you one of the very important topics. South Africa is in the top place. In quantum image processing, again, Egypt, Tunisia, Algeria, and so on. In quantum neural networks, these are the countries working in this topic. In quantum machine learning, of course, South Africa should be in the top. They have very good research group there working. So we are lucky that we are in the second place in terms of quantum machine learning. So I'm quickly will explore these topics, what we are doing in Alexandria Quantum Computing Group. And if you are interested, we can talk more about one of these topics. So I'll start with the quantum search algorithms and the quantum amplification techniques. Of course, we know the abstract problem behind this, the unstructured search problem, where we have an unstructured list and an oracle, and we need to find which item satisfies the oracle. This is the abstract definition. Classically, we know that we need n steps if we have single solution, and n over m steps or calls to the oracle, if we have m solution. Actually, this problem is general. It can be used in many different applications in computer science. The most famous algorithm, of course, we know Grover's quantum search algorithm, where he prepares superposition, then iterates the amplitude amplification techniques, the diffusion operator. This is a quantum circuit for Grover's algorithm, of course. Here is the preparation of the superposition, the oracle, and the diffusion operator. And here the marking is using the phase shift. This is how Grover's algorithm works. First, it prepares the superposition, then it starts amplifying the solution after one iteration, after two iteration, and after three iteration. And of course, many of us know if we increase the number of iterations, then the amplitude will go down again. So this is the first line we are working in quantum, in Alexandria Quantum Computing Group. Actually, we have different quantum search algorithms using what we call entanglement and partial diffusion. It is different from Grover that we use entanglement to mark the solution, not phase shift, and we will use another operator to amplify the solution using partial diffusion. Here, this is the operator we are using, and here is the amplification. So we apply the normal diffusion with the subspace entangled with state 0, and we only apply inversion pulse phase shift on the subspace entangled with state 1. And this is a quantum circuit. Quickly, I will show. I will not go in details in any of these topics. I'm just exploring what we are doing. So this is state preparation, superposition. Then we have now two subspaces representing the solution, and the oracle will switch between them like this. So applying the oracle here will switch these two states, and so on, then until we amplify the amplification. That's why, because we have two subspaces representing the solution, we resist the de-amplification behavior in the Grover. So this is Grover's behavior, and this is the partial diffusion behavior. And let me quickly show you one of my favorite citations. Actually, it has been this paper has been cited by Love Grover in his paper, a different kind of quantum search. He described this algorithm as the best quantum search based algorithm for this problem. So I emailed him to thank him about this citation, and it was really honored to have this citation from Love Grover. We used this algorithm to propose many different another algorithms with better behavior and better success probability. We also use this algorithm in the problem quantum pattern classification, which shows better behavior than other amplitude amplification techniques. We use this problem to solve, this algorithm to solve problems such as the test suite minimization problem. This is a famous problem in software engineering where we try to minimize the number of test cases and still cover all the requirement of the problem. This is a quantum circuit. We used also this algorithm to propose a quantum algorithm for set operation, which is this is a normal set operation such as intersection, union, difference, and so on. This is important. This is important in many different problems. Actually, set operations is many common in different problems. So this is the true intersection algorithm for the intersection, difference, union, and so on. We recently used this algorithm to solve or to propose answer set programming solver. Answer set programming is a technique used to solve NP hard problems such as the Hamiltonian cycle problem or the N-queen problem by reducing the problem to set formula. Then we take this set formula and convert it to a quantum circuit, and then apply our algorithm to amplify this the solution. It shows better behavior than other answer set programming solver. We also use this algorithm to enhancing security for the communication using quantum channels by hiding the message in a superposition. Here, I mean by hiding the message is to make the probability of the message zero during the communication. So if anyone try to measure the message, you will get it with probability zero. Actually, this protocol is a combination between Grover and the partial diffusion. Here, hiding the quantum state is done by the partial diffusion, and showing the hidden states again on the other side can be done using Grover's algorithm. This start actually in a line of research in our group, the quantum cryptography. We use this technique to propose quantum signature scheme using this technique, and we use it to propose a secured quantum 2-bit commitment protocol, and we use it to propose a secured half-duplex bi-directional quantum key distribution protocol. So we have this line of quantum cryptography in our group. And we are using it now to propose control teleportation, or it is more commonly known as quantum internet, where we need to communicate with some control of some server. So it is known as quantum internet or quantum control teleportation communication. The second topic, I will not go through all the topics. I'm just going to show you one or two more topics. Is the sciences and optimization of quantum circuit. During my PhD, actually, when I was designing these quantum algorithms, I was trying to find a circuit representation for the oracle. Usually in literature, we use the term black box. So what's inside this black box, which by which we can represent this problem. So this was a representation of any Boolean quantum circuit using great molar expansion. Using this approach, we can easily convert any Boolean function to a quantum circuit. But we now have algebra for representing this quantum circuit, we can represent this Boolean function with many different quantum circuits. So all these 4 quantum circuits are equivalent to each other. So which is the best based on the constraints of the hardware. So this started a new line of research in our group. This is quickly, if we have any digital circuit, you can convert it using this approach to a quantum circuit. So these are some samples of the quantum circuit. So this is the OR, this is the XOR, and this is actually this technique is widely used now in literature and sometimes without citation. And I don't mind about this as long as it is useful and can be used to solve problems. So we start to find ways to find the best representation of the Boolean function as a quantum circuit, but we start going, instead of going for n inputs and single output as a Boolean function, we start working on n inputs and n outputs. So all these quantum circuits are equivalent to each other with n input and n output, and this started a long line of research in our group. These are papers proposing methods to try to minimize the number of gates in the quantum circuit. So these are all papers in this line. I don't know if I have more time to explore one more topic, or we can leave it for the next Farai.
Yeah, you could wrap up.
If we are,
wrap up. Thank you.
I can leave this for the next roundtable or any other time.
Yes, and there's some questions from the chat. Abdelali, if you don't mind unmuting yourself and asking directly so that I don't lose the nuance that you wanted to convey. Thank you.
Hello?
Hello.
Yes, we can hear.
Yes. My question is, what program did you use to obtain the results shown in your presentation?
What program?
You show interfaces and some results. I didn't understand what was that exactly.
Okay. We use combinations from real quantum computers such as IBM. We have our own quantum simulator. I can show you. This is in-house simulator. It is available for free, and of course, mathematics is the basic tool we use to prove all these topics. So let me quickly show you our own simulator. Actually, we have version 2 from this simulator now. Still beta version, but I can share it with you if you are interested. So quickly, I will open the simulator.
So this is your custom-based simulator, or it is totally free or open source?
It is. Yeah, it is. It's free. I can send it to you to use. Many researchers in Egypt actually is using this simulator. It has been developed
so it is not about Qiskit or other or Xanadu.
Qiskit is one of our tools. We verify all our work first through mathematics. We have to prove this mathematically. Then we simulate to understand the behavior on real quantum computers and on simulators. All these graphs, if you are asking about these graphs are being done using MATLAB, based on the equations from the math, of course.
Okay, thank you.
Okay.
Are there any questions for Professor Yunus at this point? Yes, Adrian. Yeah, Adrian. Sorry for that. I know you had the hand up early on. So yes, Adrian, you can go ahead. We can't hear you yet. Yeah. Yes, Aslan. How are you? You can go ahead.
Yes, I'm good. Can you hear me all right?
Very well. Thank you. You can proceed.
Yes, thank you so much
for
Ahmed,
all
for
your reactions. You are active in reactions. So
no,
thank
I'm
you.
also running experiment here with the new AI. So I just wanted to quickly ask, thank you so much for the research. I know it's an exciting era this year. We have so much explosion in quantum. My question would be, how would you, do you integrate your quantum AI and quantum APIs? Because we now have, Microsoft Azure, quantum elements, there's NVIDIA. So what I'm doing now with my team of projects of scientists, we are taking all the APIs of the available quantum, and we are integrating with SLM, LLM, and natural language programs. So like OpenAI, Grok, all of the tools. So similar to like how Perplexity is doing, but more building towards a quantum natural language model, so we can accelerate finding new medical cancer treatment. So my question to you is, what is your experience? I know it's very difficult. What is your experience with the kind of the quantum AI? Any suggestions on accelerating the research in the
Actually,
quantum AI?
I didn't do much work on LLMs, so we are exploring this right now, but we didn't have any results in connecting LLMs with quantum computing, and this is a really exciting topic because many people publish warning about integrating LLMs with quantum computing. LLMs is changing the history, and quantum computing is changing the history. So what if we combine them together? So this will
Perfect.
be very interesting.
It'll be great to.
Yes.
I'll send you all our research and where we got
Yes,
up
very
to.
interesting. Yeah.
And the focus is on SLMs, because the small language models like 5.4 has a smaller training data, which means that you can focus on feeding it more accurate physical and the right science. So working with SLMs first would be a great idea. But I will share the research with SLM and LLM.
Yes,
and NLP.
very interesting. I will be glad to see. Yes.
Thank you.
Oh, okay. Yes, I think we have end up from yes, Prof. Conrad.
I think Adrian has a question.
Oh yes, Adrian, we couldn't hear you last time. If you can proceed, then we hear from Professor Conrad.
Yes. Good evening, colleagues and Professor Yunus. This is more a comment. I'm very intrigued by seeing that you use classical logics to kind of reduce the number of quantum gates. At least that's how I understood it from. And I'm fascinated. So I'm looking forward to read about your Reed-Miller expansions, which I don't know, honestly. But
yeah,
wonderful.
Yeah, actually, I'd like to thank you for the invitation. I hope to meet you soon. So thank you very much for this. I can send you the papers about the Reed-Muller expansions and the quantum circuits optimization. I will send it to you after the talk.
Thank you very much.
And I hope to see you next week. Yeah, thank you.
Okay, see you soon. Cheers.
Yes,
Bye.
thank you so much.
Thank you.
Adrian. Yeah, it doesn't seem to be. It seems to be having issues, I think, with the. So we will hear. You can post your questions in the chat if you can't speak. That's fine. Thank you. So to move the meeting forward.
Yeah, thank you. Thank you very much.
Yes, I will. Yes, thank you so much. I will introduce our next speaker. Our next speaker is Matt. I call him Matt. I won't mess the whole name. He will introduce himself. Accept my apologies. I won't do that fully. So thank you so much, Matt. Matt is from Seagate. He's a long-time collaborator in material science between the US and Africa and Seagate and institutions in Africa. I came across Matt's work because he published some policy perspective on, the collaboration between the US and Africa. So he's going to give us that feel of policy, of research, of industry, and how we can think about, getting this happening in quantum as well. We've got a lot of history to build up on, especially in the development of material science research on the continent, and there are initiatives already that are well established and doing so much work and that have been successful. So we wanted to hear that story of what has worked before that we can leverage and make work, in quantum. And thank you so much, Matt. You can proceed, introduce yourself fully, and then we are ready to hear from you. Thank you so much for joining as well. Appreciate it.
Thank you so much for having me. I really appreciate it. So yeah, I'm Matthew Howler. I'm an engineering manager at Seagate Technology, and I'm going to be sharing a less technical talk than the previous one, but discussing a bit more about what we can do in terms of collaborations between industry and research partners in Africa in quantum. And I'll be sharing a little bit about why those collaborations I think are really valuable, but I think even more so, what are the challenges? And I'll give an example of one of the things we've tried to do at Seagate, and you can kind of see from our perspective what we look for in partnerships, and hopefully this talk will spur some ideas on everyone's end of how we can build these partnerships. I think they can be really valuable and a great way to push this field forward. And so, again, some background on me. So I lead the Materials, AI, and Chemistry Research Organization at Seagate. So we're a group of researchers, mostly PhD level researchers who are trying to research front-end technologies that can be used in next generation devices, especially data storage. Seagate, as I'll go into, makes mostly data storage, magnetic data storage. And so trying to look at what sort of technologies we can leverage in the future to make devices that can store even more data. Obviously, we are trying to make things smaller and smaller, and so we start to have quantum effects, and there's a lot of different interesting applications utilizing quantum capabilities in some of our future technologies. But I'm also very passionate about foreign relations and collaborations, especially with African researchers. So I've written different papers on some ideas on how to create successful collaborations, as well as I've attended a couple of conferences on the continent. The pen pictured here was the National Academy of Sciences Frontiers of Science and Engineering conference in Nairobi in 2022. And so I would highly recommend, this is open to US and African scientists. So I would highly recommend, currently the call is going out for the next one, which I believe will be in Senegal. And I highly recommend people apply for it. It's a great way to meet people between the two continents and really build collaborations. And a lot of the connections I made there has helped me in the work that I've been doing. So usually when I give these talks, I'm trying to encourage people at Seagate or at US universities to fund or start collaborations with Africa. So I don't think I need to convince anyone here about the great opportunities that are on the continent in terms of resources, in terms of people, in terms of the excitement and the energy that really is going to be very powerful already, but especially over the next few decades. And so I think this creates a really unique opportunity for mutual beneficial partnerships. And this is something I'm going to talk to you about a lot, the idea of a mutually beneficial partnership. Because I think for it to work in the long term, it has to be something where both parties feel like they're benefiting. If one party feels like it's benefiting and the other one doesn't, that ends up being essentially charity. And while it can work for a bit, eventually at some point, the group that doesn't feel like they're getting anything out of it is probably going to pull back. And that doesn't create a long-term partnership that you need for these sorts of scientific developments. And especially I'm going to be talking about technology companies. How can we create partnerships between scientists and researchers in Africa and technology companies? My experience is more in the US, but this could be anywhere in the world. And so what are the opportunities for these technology companies? I put some of the logos of some of the famous ones here. But these technology companies are often looking for expansion opportunities in terms of new markets and new ideas, new people to work at their new scientists, new engineers. They're always looking for new innovative environments. And I think by including a different group of researchers, you can really spur that innovation that is so critical. Additionally, also there's bountiful natural resources. There's a lot of different opportunities for alternative energy in terms of solar. So in terms of these tech companies looking at where they want to expand, I think there is really a lot of opportunity on the continent. Of course, for African scientists, these partnerships can be incredibly beneficial. There's different knowledge sharing opportunities. So these technology companies have experience taking fundamental research and turning it into a commercial product. And that's really important because if you want to make money, increase the economy, increase GDP, you have to be able to sell the research you're doing. And so as scientists, we usually are interested in the discovery, but what brings in the money is the eventual product. So these technology companies have gone through that process. It's not easy to go from a fundamental discovery to a product that can make money, but they've done it before and they know how to transition between these two things. They know how to commercialize something. They know how to manufacture. There's a lot of challenges in manufacturing. Even if your technology is really good, they actually turn into something that's going to be mass produced and yield a high enough rate to make money. And then actually develop the technology. Sometimes it takes years or even decades to transition. And I think especially in the quantum space where there's really a lot of fundamental concepts, if we want to transition this into a product that's going to bring money into the continent, there's going to need to be some technology development. Additionally, technology companies often have more consistent revenue streams, more consistent resource availability. As we've seen in the US, sometimes federal funding can fluctuate over time, and oftentimes companies have a little bit more stability in their finances, which makes it a little bit more of a long-term partnership that doesn't change with different fluctuations in geopolitics. Also, companies inherently already have a lot of experience with global collaborations. Most tech companies are already global in nature. So unlike a university that you partner with that doesn't really know how to work with international partners, tech companies are already there. They already have the infrastructure to build these partnerships. Because a lot of times they can move much quicker than a university or a government agency that has to think about all the other ramifications. So this seems great. Like it seems like it'd be a perfect partnership between these two groups. So the question is why are there not more examples of these successful collaborations? There's definitely a lot that have been done. IBM has been doing a lot. Google has been doing a lot. But as a whole, I think it's a lot less than it could be. And you don't see, especially on the manufacturing side, many tech companies putting manufacturing sites or really large-scale operations, again, outside of IBM and some of Google, what Google's doing. And there's others too, so I don't want to dismiss it, but it's not the robustness that you see in, say, Asia or other parts of the world. So why are there not more examples of these successful collaborations if it is such a great opportunity for a win-win? And what I would say is that on the technology company side, a big part is risk aversion. People at companies are really concerned about making profit, and they're very concerned about will what they're doing lead to a negative consequence. They don't like trying new things. They like going to places they've already been, and they like working with people that they've already worked with. And in terms of on the African scientist side, I think some of the big challenges include lack of personal connections. I think a lot of people do want to collaborate with technology companies, but you don't really know who to reach out to, how to start that. What does that process even look like? Additionally, I've often seen that pitches to industry lack a discussion of how that collaboration would actually benefit the industry. Oftentimes, I think a lot of times when researchers are asking for money, they think of it in terms of like a philanthropic society where you have to talk about, you know, yourself and your work. But if you're pitching to industry, it has to be mutually beneficial. And so you have to figure out a way to talk about your work in a way that would benefit that company. So with these challenges, I think now I'm going to talk a little bit about where Seagate is and how we think about things to help get a better idea of how to pitch to industry and how to build those personal connections. So again, I'm going to briefly, this is not supposed to be a technical talk, but I'll briefly go through what Seagate does. We do magnetic data storage, and so we use a magnetic writer to write bits. As we've gone through, so this is what would be the magnetic media that's written, and then you'd have a magnetic writer that goes over the top writing that. And these are used in mass capacity data storage applications. As you continue shrinking the bits to try and store more and more data on the same platform, you start to run into challenges. And I'm not going to go into all the details, but you start to have to couple in lasers, waveguides, plasmonics, and other features to really shrink the size of the bit that you're recording. And again, all of this is done on the nanoscale. So all of this work writing and reading out this information is nanoscale properties. So we start to really encounter quantum effects at these small length scales. So we're not necessarily doing quantum computing, but we do encounter a lot of these effects. So for example, our reader, this is an area I work in, but uses a tunneling barrier to actually detect the magnetic field of the bits that we're writing. And so there's a lot of materials discovery that is needed to develop these, and especially as we build out our roadmap, a lot of it's pointing towards more quantum. So again, photonic materials, plasmonic materials, magnetic materials, different thermodynamic materials, and different coatings and lubricants. But as we look going forward, as we want to shrink our bits even smaller and smaller, quantum effects are going to have an even larger role. It's one area that we've started researching is, can we actually store data in qubits and use this sort of rotating disk platform to study, to store and read out that information. And so we have some fundamental projects with the University of Chicago starting to develop these sorts of technologies and think about what this would look like. And as I mentioned, Seagate already has a lot of international engagements. So as a company, we have a variety of global R&D and production sites that are on at least 3 continents, North America, Europe, and Asia. One of my goals is trying to see that expand to the African continent, but we obviously already have sales and stuff there, but I'd really like to see an R&D and production site there. But Seagate already has experience dealing with the challenges of an international projects. And when we expand that to include our research projects with universities, we have even more places throughout the world that we're collaborating with. Again, still mainly 3 continents, but still a fairly large number of universities that we're engaged with. Again, this is an area I think that I would love to see Seagate doing more, and I'm hopeful this year we actually have a couple of proposals that I think we'll be able to expand onto the African continent. And so you have these technology companies that have this international engagement and have this international partnership. And so then the question is, what is Seagate actually looking for in a partner? What would rise someone's application to the top of the pile? Part of my role at Seagate is doing collaborations with international partners. So we have some projects that are jointly funded, some projects that are Seagate funded. But what does Seagate look for in terms of this? And a big part of this is looking for capability that directly relates to our needs. Is this something that's going to be on our roadmap? And is it something that we can build out in the future and actually benefit the work we're doing? Also, we want to see alignment on research goals and expectations. These projects are usually on the order of a year or a few years. So do we have alignment that can actually achieve something in that reasonable time frame? Another thing we're often looking for is the tools and expertise are already in place. I've rarely seen these Seagate fund instruments, just because if we're going to fund an instrument, why not just buy it for ourselves? So usually we're funding a lab that already has the setup and just is looking to hire a grad student or a postdoc to work on some space and then work together to develop that technology. Obviously, a demonstrated record of previous work is incredibly important. If you've never done the work that you're proposing, it's hard to really make a case that you're the best person in the world. Because again, we're looking to partner with people anywhere in the world. So if you're not the best person in the world to do this, or don't have a unique capability, there's some thought that we might go somewhere else. And obviously, we're trying to look for long-term partnerships. So is there anything at the university or at the institute that would be beneficial for a long-term partnership in terms of people, or in terms of things? We want to work with people, not just have a one-year quick one and done, but really a long-term working together. And so one example of a thing we did, and this was last year, was we did an industry grand challenge. And so this was in collaboration with the NSF Compass Center, which is based at the University of Michigan, but also has sites at NC State, USC, and other universities. And we basically proposed kind of a hackathon-style competition where we had people come up with different ideas of how to solve some problem, and then have some webinars and other options to help them learn, and then propose the idea at the end of it. And the goal is to try to make this the win-win-wins that I'm talking about. Can it be beneficial for Seagate, beneficial for the participants, and then beneficial also for Compass. And so Seagate contributed a bit of money to this to do the prizes, as well as the time that it took to develop this competition. And again, this is one where the partnerships were incredibly valuable. Being able to partner with organizations like African MRS, who has a network on the continent. I was unaware of this group, so I would have also probably advertised with this group in the future, but it's trying to build those networks to help reach different people and get people excited about these topics and help generate new ideas that could potentially be beneficial both to the generator, but also to Seagate. We ended up getting over 150 signups from countries across the continent, from all different regions, a variety of PhD students, master's students, undergrads, professors, and a variety of different backgrounds, primarily material science, but we also had physics, chemistry, computer science, machine learning, and trying to really drive building out a large group of people from across the continent. And again, this was roughly a week-long competition with webinars, and then we had 48 hours for this hackathon-style competition. And we actually ended up publishing on this, I'll mention at the bottom here. So if you want to read more, I'm going through this pretty quickly. you want to read more, we have more details on what we did during this competition there. And the topic we did around cooling hard drives, so it wasn't necessarily a quantum related topic, but I think you could do this sort of format with a quantum related topic as well. And so we ended up having a virtual competition, and we had the virtual panel presentations, and we were able to award first and second place prizes. And it was really great to see all the different ideas there. As you can see, most of the judging panel was from Seagate, but we had a variety of professors from different universities in the US as well. And we had a really good positive feedback. People seemed to really enjoy the program. Also, people had a positive view of Seagate. So again, trying to make that mutually beneficial. Do they see positives in the company that's helping sponsor it? And there was a variety of learnings that we took away that I think could really help improve in the future. And a lot of these, I think, are very common, these sorts of things, but there's learnings that we could take of why some people signed up but didn't complete it, why some people thought it could be better, and so on. And I think really the big thing is, we did this last year. It did happen again with NSF Compass, but C8 didn't join this time. And I think it's really striving to create that mutual benefit. How do we create benefit for both the participants and the organization that's sponsoring it or helping? And I think on the Seagate side, how do we get better scientific ideas so Seagate sees the value in the sort of idea generation that I was talking about? And so again, so what are the steps forward? If someone does want to start building these collaborations, what can someone tangibly do to help move this forward? And so first, it's a lot about conversations and relationships. Cold calls can work, but usually it's around someone you know who introduces you to someone else you know, and you build that network. Just like this consortium, I think is a fantastic group of people and is a fantastic idea. And so especially important to know who at each company is the external research contact. Most US companies fund academic research, and so that'd probably be the budget this would come out of. So who's that person, or who's the people that know about that? And once you have that person, then you can use that contact to facilitate the relationship and develop projects. Because if you just send an email to a random person asking for money, as most of us know, it's not going to work very well. I think also from the larger perspective, we need more successful African researcher case studies where people have partnered and show that there was some win, because it'll reduce the risk. And so if I go to my boss and ask for money for a collaboration, and they say, well, am I just throwing this money away, or is it going to lead to something good? We have examples where there were clear benefit. It'll make it a lot easier for these companies to de-risk and think about, oh yeah, this is something that is going to be a win. So how do we create these successful case studies that we can publish in the literature and really get out there so people don't think of it as risky? Because I think a lot of times people in the US don't always have the right ideas about where the scientific capability of Africa is. And then especially I think it's important to hone the unique value proposition. Why should someone partner with an African researcher over the rest of the world? If they have funding for a project, why should they go to an African university versus one in Asia or the US? And I think that's a hard question to answer, but really honing what is the unique value proposition? What do people on the continent bring to the table that wouldn't elsewhere be able to bring in their research proposals? And again, if you can do that, we will move more from philanthropy, where it's just a donation, to really partnership, where it's mutually beneficial and we're able to help each other be better as we go forward. And I would say a positive example, and this is a kind of a classic one, I like to use, so Seagate has a lot of sites multiple sites in Singapore. And Singapore today is incredibly wealthy and technologically savvy. But 60 years ago, it wasn't like that. Its per GDP was a sixth of the US's. And they end up experiencing massive economic growth. And today the GDP per capita in Singapore is 10% higher than the US. So this is, and almost every technology company that I know of has a presence in Singapore. It's an incredibly small area of land. And there's many, many lessons we take from this. But I really think there's a focus on future technologies and innovation. There's a lot of partnerships with technology companies. And they also, and I'm not going to spend too much time on geopolitics, but they're able to play off some of the larger, so the US and China, their two biggest trade partners are the US and China. So they've been able to sit at the middle of this and kind of leverage these two partners off each other to get funding, to get support without fully aligning with one or the other. And they're able to stay in this middle ground and leveraging that. And I think, especially if you see in the semiconductor space, there's a lot of geopolitics that have created a challenging environment for companies. And I think Africa could be a nice spot where there is opportunities collaboration and acting as kind of this middle ground to help companies who are nervous about being in Asia, or Asian chunk companies that are worried about Europe and the US. Maybe Africa is that middle ground and can leverage that to get resources to really push that next generation of technology development to really develop into a big powerhouse like Singapore is today. So thank you all for listening. I appreciate the invitation to speak at this consortium. I'm really excited about the work this consortium is doing, and I'm excited to see where things go forward. I think there's a ton of opportunity on the continent and a ton of opportunity for collaborations between researchers around the world, but especially in the US and Africa. So I'm happy to take any questions this time, or feel free to reach out to me afterwards. I'm always interested in chatting and willing to look into collaborations.
Oh, thank you so much, man. Thank you so much. I think our marching orders as a continent are very clear from there, like, places we can learn from, the kind of things we should, set up. Yes, Adian, your hand is up. Exactly, I guess not by mistake this time, and you can go ahead and ask a question if you want, or share anything.
Actually, it was a mistake again, sorry.
No worries. I think this time around, oh, it was a mistake again.
Yeah.
Okay.
Look out.
No worries at all.
Sorry.
Thank you so much. Are there any questions
Thank
for Matt, so that we keep catching up with our schedule? You can, if you could share your LinkedIn via the chat, Matt, so that people can connect with you. I know Aditya, yes, Aditya, what I was saying correctly. Yes, you can unmute and ask. Thank you.
I just have a quick question. Is there any way to contact you?
Yeah, so probably the best way is over LinkedIn. I'm also like, I have my email. I can also share that if people are interested. But yeah, LinkedIn's usually the best way, and then I check that fairly regularly. So feel free to link in with me, and then I'll we can start a conversation there. I'll drop it in the chat.
Okay. Anything else? You feel free to post messages, like questions and ideas on the chat, so we can keep track of that, and speakers could be answering there as well, and we can unmute and give people a chance to. All right, to ask and to speak. Okay, let's move on. We're going to hear from. Yes, Benjamin.
Yeah, maybe I missed it, but I was wondering if Matthew could cite an example and of collaboration and the outcome of it. Probably I missed it. If you could repeat that, if you could reiterate that.
Yeah, so at Seagate we haven't started any collaborations. I think there's some that are going to kick off this summer. We had the Compass Grand Challenge, and so some of the people proposed different options in terms of cooling hard drives, and a couple of the students actually ended up coming to the US to do PhDs or visit programs, so there was a good exchange between universities there. I think in terms of like I said, at Seagate, we haven't done any direct collaborations yet. I think there is opportunities for that. And like I said, we have a couple of proposals in our eternal thing that I think should go through. And so then we'll have more direct results. But like I said, I think we need more case studies of wins. And so if you have good case studies, I'd be happy to hear them. But at Seagate, we haven't gotten to that point yet.
Yeah, I think he has already shared his LinkedIn, Abdelali. Matt shared. Have you shared that, Matt, yet? Yeah, I think you did.
Yep, it should be in the chat. It's the Matthew Howell.
Okay. I'll share it again. No, I could copy and share it again. I reshared that. So thank you so much. We are going now to move forward and call to the stage Dr. Mohammed Zidan. He's an assistant professor in quantum AI and quantum computing, and he's an inventor. And there are people who are asking about AI and quantum, and you may also want to learn more about intellectual property, how to be an inventor, and things in that regard, especially from an African context. In case you are doubting yourself about doing, groundbreaking work from the continent, it's actually possible. We're going to hear that from Dr. Zidan. Yeah, you can step forward, Dr. Zidan, and take it away. Thank you so much for joining. I know it's very late in Egypt, and we appreciate your patience and your dedication to make this happen. We really, really appreciate it. Thank you.
Thank you, Fry. But before I'm going to show my slide, please Should I to play the video that I was sent to you?
Yes, you can proceed. You can go ahead and play it from your end if you can.
Okay. Okay. Now I'm going to explain important topic in quantum computing, which is quantum random access memory. In fact, if we need to develop scalable quantum artificial intelligence systems or scalable quantum communication systems or scalable quantum drug discovery systems or scalable quantum computing systems, the underlying infrastructure should contain at least quantum processing unit and a main memory tailored for quantum computers. Indeed, there are many firms around the globe that trying and striving diligently to develop fault-tolerant quantum computers. However, main memory is desperately needed. This motivated us to develop our invented quantum random access memory. Indeed, in classical computers, the main memory for classical computers is called RAM. RAM, which is connected to classical processing unit through three buses. The first bus is called address bus. The second bus is called data bus, and the third bus is called quantum control. Is called classical control bus. RAM, which serves as the main memory for classical computers, comprises a set of memory cells. Each memory cell is assigned an address. When classical processing unit needs to write some data to a certain memory cell, it sends its address through the address bus and the data through the data bus and satisfies the operation as write on the control bus. Subsequently, the data is written to this memory cell. On the other hand, when the classical processing unit needs to read a data from a certain memory cell, it sends its address through the address bus and satisfies the operation as read on the control bus. Then the data is loaded from this memory cell to the classical processing unit through the data bus. However, the time complexity to read a data from all memory cells is exponential in terms in the number of classical bits which are used to address all memory cells. And the time complexity to write a data to all memory cells is also exponential. This motivated us to invent a quantum random access memory to serve as the main memory for quantum computers. Our invented quantum random access memory communicating quantum processing units through three buses. The first bus is called quantum address bus, and the second bus is called quantum data bus, and the third bus is called quantum control bus. This is the quantum circuit of our invented QRAM, which was granted 2 US patents. The first patent was issued in 2021 by United States Patent Office, and the second patent was issued in 2023. Also, we published a paper that explains in detail our invented quantum circuit and the reading algorithm and writing algorithm. Indeed, the time complexity to write a classical data to all memory cells in our invented QRAM is O of 1. And the time complexity to read classical data from all memory cells is O of 1. Furthermore, the time complexity to write a quantum data to all memory cells in our invented QRAM is O of 1. And the time complexity to read data or read quantum data from all memory cells in our invented QRAM is O of 1. This makes our invented QRAM is the fastest ever invented QRAM for both classical computers and quantum computers. And this explains why we added one in our stylist invented QRAM. Indeed, our invented QRAM is the fastest ever invented QRAM for quantum computers. Our invented QRAM increase storage space exponentially compared to classical RAM. For example, if we need to store 16 gigabytes of data in classical RAM, we will need more than 137 billion classical bits. But our invented QRAM can store this amount of data using only 43 qubits. And indeed, I'm gonna now to show a video that make a brief about our invented QRAM.
Is there any sound that we need to be hearing? What does it then? Do we need to be hearing anything because we can't hear anything? We can't hear from you yet. It's either something is muted on your end or
Stored in
yes.
QRAM.
Oh yes.
This capability is truly incredible. To implement 16 gigabyte of classical RAM, a total of 137,438 Thrinon and 53,472 bits are required. However, in contrast, to achieve the same storage capacity of 16 gigabyte using QRAM, only 43 qubits are needed. Classical RAM's sequential data access from all memory cells makes it slower for large data sets, akin to our turtle's steady plotting pace. Classical RAM operates with a time complexity of O to power n for data retrieval from all memory cells, indicating that the time required increases exponentially when reading the data from all memory cells. On the other hand, QRAM has the ability to write to or read data from all memory cells simultaneously, giving it a time complexity of O1. This constant cost of access is similar to our rocket's rapid journey, where data can be accessed from all memory cells instantaneously. In other words, you can think of classical RAM as a regular library where you check out books one by one. If you want to gather all the information contained in these books using classical RAM, You'll need to read each book individually in order to find all the desired information within them. It's a sequential process, similar to browsing through each book on the shelf to access the knowledge it holds. With QRAM, you can gather all the information contained in these books simultaneously. QRAM reads all these books at once, providing you with instant access to the information you need. The amazing capabilities of this invented QRAM make quantum computers highly efficient in information processing and will revolutionize dramatically the field of artificial intelligence.
Okay, so our invented QRAM is the most efficient quantum random access memory tailored for quantum computers. It is the most efficient in time cost. It is the most efficient in resources. It is the most efficient in reduction of noise. It is the most efficient and compatible for all quantum computers firms. It can be implemented using quantum photonics, using quantum superconductor, using natural atoms, and any quantum computer framework can be used to integrate it in our quantum RAM to build scalable quantum computers. Thank you.
Thank you so much for sharing about that. And I guess I'll start with a question. What has it taken for you to do this from the continent, just to inspire those that may be saying, you know, there's no place for quantum from Africa, like we have no starting point? How would you respond to that?
Please repeat your question again, please.
To say what did it take to develop this, you know, knowledge and capability and patent from Africa? If somebody wanted to pursue maybe dreams in that direction to also be an inventor.
Indeed, the motivation to invent this QRAM is when I was developing quantum machine learning algorithms and quantum artificial intelligence algorithms for large scale. I discovered that first thing we need to develop is we need quantum random access memory to reduce the computing time from exponential in terms of classical computers. So if you need to read a classical dataset from classical RAM, you will be limited by the complexity of classical computers. So if we need to achieve quantum advantage in quantum artificial intelligence, we need quantum random access memory to read the data according to the postulates of quantum mechanics and the rules of quantum mechanics to achieve quantum advantage in terms of time. So the first thing I think about, first we have to invent a quantum random access memory to fill gaps in quantum technology. By the way, in last 2 days, IBM announced that in 2026, they will develop their quantum computer to integrate quantum processing units with quantum main memory. And this can be achieved using our invented QRAM, because our invented QRAM is the most efficient quantum RAM invented so far. So if we need to make patents in quantum computer and make innovation in quantum computer, we have to focus in gaps. And in quantum computers, there are many gaps we have to solve to achieve quantum advantage. Before we go to develop quantum algorithms for small scale, we have focus to fill the real gaps in quantum technology, and there are many gaps must be solved before we go to scalable quantum computers. So if someone focused to try to solve some gap and some problem in quantum computing, he can develop a patent, and then if we fill all gaps, then we can go to scalable quantum computers. Otherwise, we cannot achieve quantum advantage.
Thank you for that. I think we had hands raised. Pumzile, you could come in. Then we hear from Omar, from Kenneth. I know you posted a text question. If you don't mind just asking, and then we'll hear from Constantine, and then we'll move forward to our next presentation. Thank you. Bumzile.
Hi, Fry. Thanks for the opportunity, as well as thanks to the prof for showcasing this. It's really something nice. So just two questions on my side. In terms of scalability of this, what do you foresee could be challenges if there are, and based on just the 43 qubits case, have you identified industry use cases that could actually use this on just the 43 qubits? Thanks.
So what is your question, please?
So scaling this to more storage, what will it take? Have you thought of those challenges, if there are any, as well as if we look at the current patent or the 43 qubits you have, what specifically data sets, or if we want to use data sets or use cases that are already that we have either in AI and stuff that we use specifically this to maybe process a certain data.
Thank you for your question. This is a very good question. Indeed, we implemented our invented QRAM to store 16 gigabytes of classical data. Theoretically, this 16 gigabytes of classical data that require 16 gigabyte classical RAM, we implemented using IBM Real Quantum Computer practically. And when we implemented it practically, we discovered that our invented QRAM achieved quantum supremacy for more than 100 times faster than classical 16 gigabyte classical RAM. So if you have a data set of size 16 gigabyte of classical RAM or more, you can implement it using our quantum RAM. Then we go forward to develop quantum machine learning based on the integration of quantum random access memory or QRAM with quantum processing. And we already working in some new algorithms in quantum machine learning that integrate both the quantum random access memory and the quantum processing unit. And for large scale datasets in quantum machine learning and quantum artificial intelligence, you cannot separate quantum random access memory from quantum processor. Why is this? Because we have entanglement. Classically, you can go to develop your classical machine learning without considering your hardware, without considering what is your quantum processing unit and what is your random access memory or main memory for classical computer, because there is no entanglement in classical computers. But if we need to go to scalable quantum machine learning, we need to integrate both quantum processing unit and quantum random access memory in our quantum machine learning algorithm. So we have to develop and devise our quantum machine learning model and algorithm to integrate both quantum processing and quantum random access memory due to the quantum entanglement phenomena. So before we go to develop quantum machine learning, we have to devise our quantum machine learning to have quantum random access, because entanglement that created due to applying some unitary transformation on quantum processing units and read large scale data set from quantum.
Yeah, thank you. Omar, Kenneth, and Constantine, Tiamu, can you just do them quick so that we can run and catch up with our, sorry for that. Thank you.
Hello, Dr. Zidane. I'm Omar Sofi. Perhaps you know me, and I'm from area.
Nice to meet you. Nice to meet you.
Yeah. So I only have one question. When you deal with the quantum transformation or the quantum transportation of data, like does it happen to have some loss of information during this transportation or transformation processes?
I can't understand the question.
So when the data becomes scalable, we know that it happened to have that there is some information lost during these processes, like when trying to
No, there is no information lost. There is no information lost.
Mhm.
Indeed, there are many challenges. So far, we didn't have fault-tolerant quantum processing units. We have noisy systems, but indeed, information didn't lost. But when we try to apply some transformation, for example, if you going to apply Grover algorithm, there is a new challenge appear. When you read data from quantum RAM, you didn't read data as classical RAM. Actually, when apply some algorithm for Grover algorithm, so the data is are not lost, but data is behave according to quantum computing postulates. And there are many challenges appear to us that we have to solve it. Information didn't lost, but information is transformed in superposition, and this make a new challenges that we cannot face in classical computers.
Okay, thank you.
Thank you.
Yes, thank you. Yes, Kenneth and Constantine and the TMU.
Yes, thank you very much for that presentation, Mohammed. It was really interesting. So my question is, so for the QRAM, when you're storing your data, I don't really understand how the hardware works, but like how long does it take before it decoheres? Like what's the decoherence time? Yes, that's pretty much my question.
Okay, this question is a very good question. Indeed, our invention, we invented our QRAM as a quantum circuit for fault-tolerant quantum processing. So we didn't care about the challenges that are appearing now in quantum hardware. We invented the quantum circuit to make it compatible to all technologies, to make it compatible to photonic systems, to superconducting system, natural atom system. So we didn't care about the noise. We didn't care about the decoherence. We invented for fault tolerance. So when fault tolerant quantum computers is available, our QRAM will work with no noise, with no any. We left this challenge for quantum computer to solve it, and according to IBM, this will be available by 2029. So we didn't care about the coherence time. We didn't care. We only focus on our quantum circuit and implement quantum circuit for fault-tolerant quantum computers.
Okay, thank you.
Yes, Constantine.
Yeah, thank you, Dr. Sida. Good presentation. My question is, please, do you have a design quantum circuit for that algorithm? And second question is that, like,
Quantum
how many
circuit? Quantum circuit?
Yes.
Yeah.
Yes.
We invented the quantum circuit. Yeah.
Okay. Please, if you can still display the circuit, let me fit. And secondly, I want to ask, like, how many number of qubits have you tested, and how efficient is your algorithm? And is it in the polynomial time or an exponential complexity algorithm?
Okay, thank you for your question. This is the quantum circuit of our invented QRAM, and the time cost is O of 1. The time cost to read data to all memory cells or read data from all memory cells is O of 1. So this makes it the fastest ever invented main memory for quantum computers. According to how many qubits, we invented our QRAM to work in arbitrary number of qubits. We invented to work on fault-tolerant quantum computer, so there is no limit. Any firm, any company can take our quantum random access memory and when fault tolerant quantum computer is available, you can develop quantum random access memory using our cell kit for any number of qubits for address and any number of qubits for data.
Yeah, and would you allow me to share the link to the video in the chat? The video that you played.
Feel free. Dr. Fry will share the video of QRAM and inshallah, maybe next month we will make a tutorial and a summer school in quantum.
Thank you so much. And I think thank you so much for your presentation, for the questions. You can keep the questions coming on the chat with time. And I want to invite the community from Nigeria to share with us their progress, successes, and next steps and the vision for quantum in Africa as well. So thank you. And let's move on. Appreciate your time. So yeah, let's have the community from Nigeria. I don't know who's taking the stage. Kenneth, Ini, Tanito, and the whole crew. Okay, I can't hear from any of you yet.
I think Ini
is one man to take the stage.
All right,
I'm the one to present.
Okay.
My slide will soon come up. Yeah.
Let's do it. Let's do it.
All
Thank
right.
you. I'll be muting
right.
myself. Thank you.
All right. Just a few seconds, please.
Yeah, we can see your screen when you're ready.
Okay, I'm trying to go to the first page. Okay. Okay. Hi everyone. Yeah, my name is Nigeria. So first and foremost, thank the African Quantum Consortium on this day, because with what the Prof has presented so far has given us more motivation and hope that something good can come out from here. And also, based on what I do, what CGET presenting, my vision is having the same vision with what the CGET is having, because as a preventive maintenance engineer and with proper time management, I'm also doing quantum. I collaborate with the universities and colleges to create awareness in the field of quantum technologies. So we in Q Nigeria, this is how my slide will flow. It will be the introduction, the key programs, and their impact, challenges, current programs, quantum roadmap for Nigeria, call to action, future plans, and conclusion. Q Nigeria was founded in 2021. And what was our aim? Our aim is a grassroots initiative dedicated to bridging the quantum digital divide in Nigeria and Africa. The vision is to democratize quantum education and innovation in Nigeria and across Africa. Our wider mission is to raise quantum literacy awareness, building a sustainable community of quantum learners and professionals, and enable participation in global quantum discussion and collaborations. Okay. Now, over the past few years, since 2021, we have had programs with the support from IBM, QWall, and other Womanium, and other global bodies. Then in 2021, which we had the first Qiskit 4 Fest, on-site Qiskit 4 Fest in Nigeria. That was in Uyo. After this slide, you will see the next one that put the picture that the first Qiskit 4 Fest that we had. I was a speaker. Then we partnered with the Start Innovation Hub to do the events. Then so far the impact created since we started, we have had 87 plus community members and more are still joining. We have trained 100 students plus. We have participated in 2 universities in Nigeria. So sorry, the network is bad here, so I'm trying to, okay. Okay, this is the picture of the first Qiskit 4 Fest we had in Nigeria. The key events and their impacts. Like I said earlier on, that Q Nigeria was launched in 2021 to put quantum education on Nigeria's STEM radar. We had participants during the Qiskit 4 Fest. Participants built and ran quantum circuit on their real device. We have had outreach programs to create awareness, universities, colleges, and local communities such as in various cities such as Uyo, Ibadan, Suka, Akure, Lagos, and Jos. So Quantum Africa, we have also had a workshop that was last year where different countries in Africa came together to train wider audience of students and quantum enthusiasts in quantum programming, quantum computing, and programming. And that was done with the support of Q World. Though, despite what the effort we put so far, we've had challenges. We've had such as low quantum awareness in academia. We have funding constraints for education and outreach, lack of national quantum strategy until recently, limited access to quantum computing hardware, volunteer burnout, and infrastructure gap due to internet and electricity. Currently, we have some programs running in Nigeria. We have 2 active and 8 in progress quantum curriculum pilot STEM for department. We're also currently working hard to see how we can have women and quantum mentorship and advocacy programs. Currently, we have 2 research projects ongoing, one with XPRIZE. And the good thing about one of the projects is that it's in line with the Sustainable Development Goal of the United Nations because it has something to do with renewable energy. We are looking at the possibility how we can enhance the design and the manufacturing of solar cells. So with the help of quantum technology, we'll see how we can enhance that. The project is ongoing. So our targets, we have 3 location targets for quantum cities average. I heard at the beginning of the session, they were asking Nigerians are not on the quantum city map. I had raised it some times ago when we had a meeting that I have registered for the quantum city price, but I still don't have our points on the map. And I sent a message, but up till now, no response. Maybe after the presentation, Dr. or Professor Junis will give us more like why that is not happening. Thank you. So I move to another slide. So so far we have 2 universities that are having quantum clubs in Nigeria, Ibadan and University of Uyo. So currently we have other universities that we are engaging year in, day out to make sure that such clubs do exist in their universities. We have quantum roadmap for Nigeria. We have 4 pillars that we've want to design the quantum roadmap. We have in education, we intend that courses in all tertiary institutions to be implemented in 2026. We have research groups focus on material science, chemistry, cryptography, communication, established quantum labs that will be focused on research. Under innovation, we intend to support startups in quantum-inspired fields. Good enough. Seagate is here. We intend to work with Seagate to achieve this, our goal. And then policy, National Quantum Forum and Inclusion in Digital Nigeria Strategy. As a quantum roadmap for Nigeria from 2025 to 2030. Collaboration and recognition. We are currently collaborating with African Quantum Consortium. We partner with QWall, which is our main body. We intend to collaborate with Pan-African Quantum Talent Programs. So with the experiences we've had so far and the challenges, we need to partner and sponsor for volunteer to support Q Nigeria to help us integrate quantum into our national curriculum, to join regional and global quantum collaboration to make a quantum a reality. The future plans, we intend to launch high school quantum clubs this year. We've started the engagement. Now we intend to have a national quantum festival next year to create more awareness to key stakeholders. Then also, a quantum AI innovation lab, then quantum research, open journal, and access. Then in conclusion, if we must lead in the 21st century digital economy, then we must prepare to lead in quantum readiness. Q Nigeria is committed to grassroots engagement, talent development, and international collaboration for quantum-ready Nigeria. Having said that, I want to remind the audience or the participant of this great occasion that today, if we look back history, was the day that UNIFAC 1, that was 74 years ago, that was unveiled to the public. So it's I would say, today with this partnership and engagement that we have started, that something great will come out from this roundtable discussion. Thank you.
Thank you so much, Ini. And yes, this is really a beautiful story. Growing quantum through the pains that it takes to get there. And thank you so much for sticking with it and for expanding access and education and doing what you can with what you have and where you are. And we need more of that across the continent. On the city prize, so there's the city side and there's a city prize. So the city prize, I think Professor Yunis commented that there's a lot of exciting things that he's seeing on that back end, and those things don't come out on the public platform. But the ones that come out on the public platform are the Quantum Cities one. So if you've got hosted any event and you submitted it under the cities, it should be reflected. If it is not, for sure, we are happy to follow that up during the bi-weekly meetings and talk about why that is the case. I guess it's so late in Egypt right now. Some of our attendees from that part of the continent have had to jump out. So if Professor Yunis is still here, he could comment about it. But in case he has left, it is because it's beyond midnight now in Egypt. So yeah, thank you for your presentation. Really beautiful. I think a lot of us who were sitting by the fence and thinking that we can start, we don't have a starting point, we are, there are day-to-day problems to solve. We can see that, yes, with that, we also want to reduce the gap. We don't want the gap to keep on widening. So we have to be using a two-pronged approach where we solve problems of today and we also, look at the problems of the future that we need to help solve, and we do both. So that is a very important approach, I think, and we need that. That is the most practical approach at this point. All right, thank you so much. I think we went a bit over, and if there are any questions, I know there was somebody who had their hand up. Let me see, who was that one? If you had your hand up earlier and have lost track of things, please come forward, ask any questions or your contributions at this point. Thank you. Because that hand went down later on, so I don't have a feel of it. Okay, so with that, I guess we are getting to the end of this event. Thank you so much for your time. And to just recap, we came together as a continent in a powerful way. Thank you so much. We could not have done this without you. We heard about the engagements that the Africa Quantum Consortium has been moving forward across the globe. We are growing and very fast. And we are part of conversations that are really important and key. The idea is this year of quantum, the International Year of Quantum, there are many initiatives that are focused on Africa that we should take advantage of. So let's put our hands on deck. Let's collaborate. If you are from any country in Africa and you want help to get started, please let us know. We've got a lot of experts available to help. We've got a lot of resources we can share. We've got connections we can link you with. We want to hear from North Africa. We are setting up hubs across the continent. Thank you so much, Professor Nindila from Nairobi. We appreciate that you could join us. So we are setting up hubs across the continent in North Africa, West Africa, East Africa, and Southern Africa. And then from those hubs, we are going to expand our quantum efforts locally and make people talk to each other, help each other, because you understand the context, you are neighbors. So we want to spark that conversation and help you to succeed from wherever you are. So if you can help us translate our content in Arabic, in French, in Twi, in Swahili, in Zulu, in Shona, in local languages, I don't know, I can't represent all of them. But let's do that. Let's make quantum accessible. Let's make the education. Let's make the news. Let's make the opportunities that are available in the ecosystem available. And let's look at the hard problems. So we had yesterday and today, we had a happy hour and we heard about it today again, that there are hard problems in quantum that we can solve from the continent. And the people that we had talking about developing intellectual property in software and even in hardware in some cases are actually located and based in the continent right now. And they've done their work from the continent. I did my quantum from the University of Wits in South Africa. I have had access to a characterizing system, to synthesis chambers, to magnetometers that are comparable to where I am now in the US. So I started doing quantum in Africa. And that's where I really cut my teeth doing quantum. So we can do that. And we can expand. We are actually thinking, the reason why we want to build an ecosystem is to expand that opportunity and to expand these collaborations we can do. You've got the hardware, you've got the clean room, I've got ideas on the software, I can do the designs, I can build community, I can educate, I can do the startup and build value, I can invest, I'm the investor. All these partners can come together and we can build an ecosystem in Africa. And we can only hear, from here we heard about the vision for research and development and innovation hubs on African soil, in African countries. And there are people here attending this meeting who are thinking about these ideas, who are taking steps today in their small way to build this opportunity. And it starts today in those small steps. And as we collaborate and tap on this, it's distributed strength, including the partners. We heard from partners in industry in the US, and we are going to hear more even in Europe. It is well available to support. We have collaborated with Africa before, because at the end of the day, quantum is a global effort. And we have to come in there, shape it using our capabilities. And the partners are also going to rely on that to make the technology move forward. So there are many entry points for contribution. There are things that we can do and that we are already doing after all, that we need to make the world know about. And that's the role of the consortium. We are an ecosystem enabler. We are neutral. We want to amplify your voices. We want to promote all of you. We want to showcase your work. We want to build the partnerships that can help you. We want to change the socioeconomic outcomes and socioeconomic, foundation for the continent. And this is the time to do it. There are many things that are, coincidentally coming together, including the diplomatic shifts, the discovery that we have to leverage our position, the quantum and AI era, and there are many things that are coming together. I can't list all of them. There are so many, and this is the right time. There will always be that window of opportunity, and I feel this is the window of opportunity, and we have to grab it. It is also the International Year of Quantum, and most of the focus is on the Global South. And the 2 International Year of Quantum global events are happening on African soil, meaning that experts and all the critical stakeholders who are shaping quantum and who are going to even invest more to shape it in the future, are going to come on African soil, meet us, and we wanted to hear from us, wanted to see how prepared we are, want to see clarity, want to see strategy, want to see this path forward that we present as a continent, and so that they know very clearly. Even the G20, for example, is also happening in Cape Town. I know, or I think so. I think it's happening in Cape Town. So all these are opportunities where the focus is on Africa. So we have to show what we are doing. And if there are people who want to partner us, they have to know our needs very clearly and know how they can help. And we can get to build this ecosystem and make things happen. So really, really super proud about the future of the continent and the things that we can do. And we want to be able to go to all these forums to represent you well, and we are collecting information about that, be on our platforms, respond to our calls to action, because we want to go to these forums with a strong, front, a strong presentation, and with a strong foundation we can stand on to be very clear about what Africa needs, what should happen for quantum to work for Africa, what should happen for us to reduce that gap in innovation, in technological development, in education, in economic development as well, as we go forward. And we have to change that from here today. And we are the people who have to do it. And thank you so much for joining us today and adding your voice to this conversation. I hope to continue hearing from you on LinkedIn, on the happy hour, on the bi-weekly meetings. We are going to have another roundtable in September. Around there, we're still fleshing out details. We're going to also, change the time so that it can be more convenient for most of us. But the next roundtable, to just give you a preview, is going to be focused on startups. It's going to be focused on industry. There are a lot of startups that are coming together, coming up in the continent. Some are being incubated outside. Some are going to be incubated, on the continent. Got some investors who are setting up some funds for deep tech, quantum and AI. And we want to hear from all these. And they're going to be sharing their vision for Africa, what they're doing, and where they are, and the kind of solutions they are exploring. And we want to build an ecosystem. Like I said, we want to build value on the continent. We want people to exchange transactions, to transact and exchange value and build an ecosystem, create jobs, change economic outcomes, support our startups, invest in them, and build this ecosystem where value is exchanged and the economics of the continent begin to change as well through technology, quantum and AI. And I think this is the time. It has never happened this way. And it's something that we have to take advantage of. So with that, I will give it up to Benjamin and Temitope to wrap this up in case I left out something. They've shared links with you on things that you should take action on, and would appreciate your support and your responses. Otherwise, thank you. I know it's late for most of you, especially on the continent, but I can't thank you enough. And we are forever grateful for your support and for showing up today. So yeah, thank you. Over to you, Benjamin and Temitope, to wrap this up in case there's anything that I missed. Otherwise, I'm done and I'm beyond grateful. Thank you.
Yeah, thank you I'm going to keep it real short. Yeah, so so far you have seen that there's been a lot of great progress that's been made collectively as a community, and that's because of your continuous presence, your continuous support. And so we want to take this really far and to make it really impactful. And so yeah, we would be calling for more hands on board and to contribute to all that is being posted. The white paper we have, seeking opinions on the white paper that's been developed. We have forms that have been shared for to collect more information. And so let's put our hands on board. If you have any other thing, you could email the consortium. Maybe there is something that you can contribute to that has not been mentioned. You could just reach out. We are very much open. And with that, thank you for joining today. And apologies for the early hitch-ups on my end. Hope to see you in our next roundtable.
Thank you, Pumzile. We could not have done it without you. Thank you, Edmore. Thank you, Gospel, Pesedi, Victor, Mohammed, Mai, Imanshu, Tiamu, Tenito, Omar, Tunde. So many of you. Daniel, who else? Yara, yes. Thank you, Lambu, JG, Konstantin, Benjedi, Aslan. Thank you for the engagement and for sharing a lot of resources and opportunities. Anikan, Adrian, Abdelali. Thank you so much. We really appreciate it. And thank you, thank you, Benjamin, for holding forth. Omar as well. I know we don't have Abdul Salam here, but yeah, thank you for all you do. Whenever you can do it, I really appreciate that. Can never have been able to get this far without your support and your belief in the vision for quantum in Africa.
And thank you to Ini for the updates on the Nigerian side. Yeah, we're glad that something is cooking.
Yep, we love that. We always love it when things are happening over there. So next time, yeah, we're going to hear from our friends from the French-speaking world. We're also reaching out to people in the Portuguese-speaking countries. In case you know someone, please introduce us. We all, like we're saying, we want this year to end when every country has had an opportunity of talking quantum. So yeah, last time it was fun to talk to people in Banjul, the Gambia. I'm also going to talk to people from Mauritania, which is super exciting. So we want to keep on hearing from more and more people from across the continent. Cape Verde, Guinea, Guinea-Bissau, Equatorial Guinea, the Central African Republic, Burundi, Rwanda, Burkina Faso. Yes, here you go. So just as an aside, I know Benjamin was actually in Burkina Faso recently. Benjamin, tell us about your visit to Burkina Faso.
Yes, I was there recently. And by the way, I just stay very close to the border. It's a ride away, less than an hour. Yeah. So I was there on food tourism. And yeah, I ate what did they call it? Mbalango. I don't know whether any Mbalango, it's some roasted meat. Oh my goodness, so spicy. I loved it. Yeah, I didn't go so much deep into Ouagadougou. It was a ride on the bike, so I just got in and got some stuff and got back. Quite exciting, yeah.
Sure. Next time, let me know. Okay.
Okay, yes, you let you know. I challenged him to come to Ouagadougou, so feel free to connect and make that happen. He can bring you the Africa's qubit. We actually want to take Africa's qubit around Africa.
Okay, let's take it on a tour.
Yeah, Africa's qubit tour around Africa. That's going to happen. We've got big plans with that qubit. You will see it in your city soon. It will start by going to Ouagadougou.
Yes, I will getting you in touch with you soon, because one of the big universities in Burkina Faso asked me to stand an event, quantum computing. Probably I will contact some of them, some of you, for this event.
I'm sorry,
Yeah.
Farid.
I'll be
Cut.
wrapping up and walking outside so we can keep the conversation going as we drop off one by one. That's fine. So Benjamin, keep at it. I'll be walking out of here.
All right then. All right then. Tammy, do you have some last words?
None.
Okay. And we've got Yara here who anchored the last session of the happy hour. Yeah, Yara.
Yeah, thank you so much for that. That was so great.
All right, thank you for anchoring it. And yeah, we hope to see more people join and to also equally anchor it. And by the way, you don't need to prepare so much for that particular happy hour. It's usually unstructured. We don't have slides as you're showing over here. There are no technical stuff. It's just come and talk about what can come up. Okay, so we could talk ranging from policy, international stuff, to things related to quantum, people's work life. We've got someone who was sharing a lot about going from one job to the other, was saying that she literally went to interviews while working. So like on a lunch break, she goes for work interviews. That was quite interesting to me, how you could be working at a current job and then you go out on a lunch break to another work interview. So yeah, such conversations and collaborations, connects that you didn't know of. For example, hopefully Constantine and I will be meeting hopefully soon. Yeah, so such do come up. And so would be expecting you on Friday. Yep. All right then. So that's it from my end. Oh, yeah, tell me.
Yeah, I'm just saying bye, everyone.
All right then. Right, bye. Have a great weekend. And to you, if you're gonna sleep, a good night. Bye.
Thank you so much. This was great.
Bye.
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 Bye bye. Good night.